to the next session on NoHub series. This video is all about stick diagrams in VLSI design. As the fabrication process becomes more and more complex, there is a need for the VLSI design engineer to understand every minute details of the fabrication process. One such popular method of symbolic design is stick layout. In this, the designer draws a freehand sketch of a layout using colored lines to represent the various process layers such as diffusion, metal, and polysilicon. The main advantage of this symbolic approach is that the designer does not have to worry about the design rules because the compactor ensures that the final layout is physically correct. Let us now start this first part of the video on stick diagrams with a brief introduction and what are the color codes that are used in the stick diagram and how a transistor is represented and what are the general design rules to be followed in a stick diagram. Finally, we will conclude this video with a simple example of a CMOS inverter and try to understand how to represent a CMOS inverter using stick diagram. Stick diagrams are used to convey layer information in a chip. They typically act as an interface between the circuit and the layout. In stick diagrams, each and every layer is going to be represented using color codes or striped patterns. The size of the patterns, width of the layers, wire length are not mentioned in a stick diagram. Stick diagram helps the designer to plan the final layout and the routing. For a chip designer, all the CMOS designs will consist of the following layers. So these are the very important layers which we should concentrate while drawing the stick diagram. The first one, we will always start with setting up the substrate or wells of P-type for NMOS transistors and N-type wells for PMOS transistors. And then we'll move on for fixing the diffusion layers, which are generally called as active areas. And then we have polysilicon layers, which form the gate terminals of all the transistors. They are also used as interconnects in some designs. And then finally, we will have metal interconnect layers and contact wire layers for providing interlayer connections. Next, we will move on for the color codes that are used in the stick diagram for each and every layers. This tabulation will give us the complete detail about different layers that are existing in all the CMOS designs and its corresponding color codes and its corresponding striped patterns. Suppose, for example, if we have to draw an N diffusion layer, we use green color, and if you're going to use patterns, then it should be a simple straight line. And then for P diffusion layer, either yellow or brown color can be used. For polysilicon layer, which means the gate metals are always represented using red color. And then we have metal 1 represented using blue and metal 2 represented using magenta colors. And then we have contacts and taps with which we try to represent all the interconnections. So for that we use black color. Since the background here is black, I have represented it in white color throughout the stick diagrams. And especially we need to understand it is very important to have the VDD and VSS, which means the power supply and the ground lines, which are the metal layers, and therefore they are represented again using blue color. Next, we will move on for how to represent a particular transistor, either NMOS transistor or PMOS transistor, because that is what we are going to repetitively use in all the CMOS designs. So therefore, we will understand how to represent an NMOS and PMOS transistor using color code and stick diagrams. Here is the NMOS and PMOS transistor representation using stick diagram, where I have used striped patterns and also the color codes. When a particular polysilicon layer, so which means here the polysilicon layer, which is denoted in red color, is the gate metal layer. So this polysilicon layer, whenever it is crossing an N diffusion layer, so which means we know that an N diffusion layer should be represented in a green color. When this polysilicon red layer is crossing an N diffusion green layer, it represents an NMOS transistor. Similarly, for a PMOS transistor, it is when the polysilicon red color layer crosses the yellow or the brown color P diffusion layer, and then it is representing a PMOS transistor. So now we have understood how to represent a basic NMOS and PMOS transistor using color codes and striped patterns. And now we will move on for the actual design rules that are involved in depicting the stick diagrams for any CMOS logic design. The design rules are going to be very simple. It is going to be the similar procedure of how we try to implement the schematic representation of any CMOS logic design. We start with VDD, which means the power supply, and then we have a pull-up network, which consists of PMOS transistors, and then we will have the common drain terminals, which we take and represent as output, and then finally we'll have the pull-down network, which consists of NMOS transistors, and at the end we have this VSS layer. So the same thing, but for the stick diagram, we are going to fix certain things at the earliest. So the first point is we need to draw the VDD and VSS, which means the power supply and the ground layers with a sufficient space between them. So you're just going to fix the VDD and VSS layers. And next we draw the NMOS and PMOS diffusion layers, and it is very clear that we represent an N diffusion layer using green color and P diffusion layer using yellow or brown color, and then form the NMOS and PMOS transistors by placing the polysilicon layer. So which means this polysilicon layer is a red color layer, and then we connect the drain terminals of both NMOS and PMOS together using a metal layer. So wherever we use a metal layer for interconnections, it should be represented using blue color. So all the color codes are also important. Now we need to connect the source terminal of PMOS and NMOS transistors to VDD and VSS power rails, again using a metal layer, which means the blue color layer. Because PMOS, the source terminal, has to be connected to the VDD power supply rail, and NMOS transistor, which means the pull down network, everything should be connected to the ground rails, which means the source terminals of NMOS transistor has to be connected to ground rails. And again, for all output and input interconnections, we use metal blue color layers. And finally, we place a contact cut at points where two different layers are connected together. So that is represented using black color. Next, we will take a simple example. To start with, we have CMOS inverter, and let us understand how to draw a stick diagram for the CMOS inverter. Now first, here I have drawn the symbol schematic of the CMOS inverter, which means the static CMOS design of CMOS inverter, where we have the common gate terminals connected together for representing an input, and common drain terminals of this PMOS and NMOS, and we have taken the output, and the source of PMOS is connected to VDD and the source of NMOS is connected to VSS. And this is what we are going to represent using stick diagram, which is going to exactly convey the layer information in a chip. So now what are the layers? We know that there are different layers, which means N diffusion, P diffusion, polysilicon, metal, and then we have contacts. So all those things are inbuilt in the schematic diagram, which is not visually seen. So that we are going to depict using stick diagrams. Okay, so this is just an interface between your circuit and the physical representation of the circuit. So where each layer we have different color codes. We have seen all those color codes, and now we are going to represent this particular CMOS inverter using all those color codes to understand the layer information that is hidden in the schematic circuit diagram. So now, as per the first rule, we understand that we need to fix the VDD and VSS layers with leaving a sufficient space between them. And I've also mentioned that since both of these VDD and VSS layers are going to be metallic layers, we again use blue color. And next what we need to do is the second step, where we need to fix the N diffusion and P diffusion layers. For N diffusion layer near the NMOS transistors, we use green color, and for P diffusion layer I have used an yellow color. Okay, so now these diffusion layers are generally nothing but your active areas where you are going to take or give interconnections with your polysilicon layer. So I have also told that when a polysilicon red layer is going to cross the yellow color P diffusion layer, then it becomes a PMOS transistor. And when this polysilicon layer crosses over this green N diffusion layer, then it becomes an NMOS transistor representation. So step 1, fixing VDD and VSS layers are over, and step 2, fixing the N diffusion and P diffusion layers are also over, which we have depicted with green and yellow colors. Now the third step says form the NMOS and PMOS transistors. So using the P diffusion and the N diffusion layer and bringing this polysilicon layer, we can create NMOS and PMOS transistor. So now what I'm going to do is just bring this polysilicon layer. Here we can see that this is going to represent the gate of PMOS and this is going to represent the gate of NMOS. Since gates are polysilicon layers, and we have represented that using red color, and the interconnection where we need to join both these gates of NMOS and PMOS, right? So that is also done almost with the polysilicon layers, because we are just extending the polysilicon layer so that both the gates are getting connected. And we need to take the input line, where I have also clearly mentioned that both the input and output lines are represented again using metallic layers, where metallic layers are again represented using blue color. So now just bring this polysilicon layer, which has to cross over this P diffusion layer to form PMOS transistor. This has to cross the N diffusion layer to form the NMOS transistor. Now the fourth step says connect the drains. So now you understand that this is a transistor. The transistor one end is going to be this gate, and this end is going to be the source, because we obviously know that the source of this P diffusion layer has to be connected to the VDD layer, which we have fixed earlier. And similarly, the source of NMOS is going to be here, because that has to be generally connected to the ground rail. And therefore, the left out terminal is going to be the third terminal, which is the drain terminal of PMOS and NMOS. So the fourth step says connect the drain of both PMOS and NMOS transistor, which means the green and yellow has to be connected together, but they cannot be connected as such. You cannot join them directly. As per the stick diagram rules, the N diffusion and the P diffusion layers must be again joined through a metal layer. So the drain terminals are connected together using a blue color metal layer. Now connect the source terminal of PMOS with the power supply rail, VDD rail, and then the source terminal of NMOS with the ground rail. So just use again the metal layers to connect the power supply and ground rails. Once all these things are done, the outputs and inputs, they again use metal layers. Since drains are connected together using metal layer, simply by extending this metal layer will give the output terminal, which we are going to represent it as out. And for the input terminal, again we have used a metal layer to the poly layer. In some designs, polysilicon layer itself is extended and used as the input. Now the final step is to place a contact cut points wherever we have two different layers that are connected together to indicate the interconnections. So from here we are going to just start giving the contact cut points. So this completes the final stick diagram representation of CMOS inverter. To summarize the first part of the video on stick diagrams, we have understood clearly about how to represent a stick diagram for a basic CMOS inverter. That is the first point. And before that, to draw that particular stick diagram, we have understood certain rules are there, and we have seen all the design rules step-by-step procedure, and we have also seen the color codes to represent all the layer information that is hidden in the schematic diagram. So which is basically a stick diagram is a cartoon of a layout. In the upcoming videos on know-how series about stick diagram, we will understand a very peculiar method which is called as the Euler's method, which is very helpful for drawing the stick diagram for any given Boolean logic function. So we are going to see those particular methods, how to represent an Euler graph, how to find out a common Euler path, and how to implement them for a Boolean logic function representation using stick diagrams. Hope you all have enjoyed this video on stick diagram introduction. Catch you all with the next part of the video soon. Thank you all for watching this video through Electronics Insight channel.